So I know I keep using the term octet rule, but we do have some exceptions, and our exceptions occur in a couple of groups, groups 2 and group 3. If you'll note, a lot of the elements in groups 2 and 3 look like metals and they shouldn't be covalently bonded. And I hear you, but it happens anyways. So in groups 2 or 3, so if we take a look at our periodic table, this group right here and this group right here can have incomplete octets, meaning less than 8. Also, we can have down here, as we go down in our periods, we can have more than a hypervalent or an expanded octet. And the only way to do these is just to do these, so let's consider BeH2. Beryllium is in group 2, so it's got 2 electrons, plus 2 times 1 from hydrogen, giving us a 4. So there's no way that's going to obey the octet rule, and we simply have that. It does actually exist. So, incomplete, how do you know? A, not enough electrons. B, it's in group 2 or 3. Now, boron. Boron is in group 3. Boron does some very weird chemistry, and one of the things it does is that it has incomplete octets. So if we look at this, boron in group 3 plus 3 times 7 for a total of 24 electrons. I know you're going to look at this and say you can get complete octet out of it, and you can, but it doesn't happen. So this is what happens. Boron is going to single bond to each of these fluorines. We're going to take and put the remaining lone pairs on the outside, same way we always do it. And when we stop here, after a total of 24 electrons, we are going to try to, withstand the urge to put a remaining 2 over here as a double bond to the boron, and boron will stop at this. Now, when we get to our next section on formal charge, we will discuss the policy and the rules that we have for figuring out for sure that this stops here rather than making a double bond. Now we have some weird ones, particularly with nitrogen, where they have an odd electron. Odd electrons on them are free radicals. And if we have an NO2, so if we have NO2, we're going to have 5 plus 2 times 6 for a total of 17 electrons. So we know we're going to have 1 left over. And when we bond this, and we try to at least make some of this work, if we double bond to one oxygen and single to the other, and we put our electrons on, that's going to give us a total of 8 for each of these oxygens. It's going to leave us with 1 left over on the nitrogen, which is going to give us a total of 17. If I tried to bring in this pair here, we would have too many on the nitrogens. It cannot do that. Nitrogen will tolerate 1 electron here, but it will not have an expanded octet. So does it do this? It does, but it also tries to find another one in the atmosphere and make this stuff, which is N2O4. So these exist with odd ones. If you find yourself with an element where you've got odd things, like for example, NO as well, just going to draw it out to make it work and make sure that you do not expand. So do not put more than 8 electrons on any one of these elements. We'll see the expanded ones in a second. All right, exceptions to the octet rule. Now we looked at incomplete. Now incomplete, they're very rare, and truly they're mostly things like boron and maybe gallium or indium down here in group 3 with the occasional beryllium in this. So we're looking at groups 2 and groups 3. The other exceptions to our octet rule are expanded, meaning we're going to have hyper, which is more valent, more than 8, which means our quantum number has to be greater than 2. So what does this mean? Off of our periodic table, draw this out, and we look at our quantum numbers. And we start out over here where we have our boron and our carbon. This is corresponding to a quantum number of n equals 2. These guys do not expand. The only ones that expand are when we get down here to n equals 3 and greater. So it's a really short list of elements. It's going to be things like phosphorus and sulfur and chlorine. Argon doesn't tend to do it. Arsenic, selenium, bromine, krypton, antimony, tellurium, the T, iodine and xenon, and then probably or possibly radon. But we in general ignore these guys because they're radioactive, and so our list is really only these elements right here, where we have an outside quantum number of 3 and greater. So what happens? What happens when we build these is that we take a look at our formulas. When we have an x, y to the n, we take the x and put it in the middle, for example, the phosphorus, and we're going to put all 5 fluorines around this. And when we do this inherently, we're going to have more than 8 around the central atom. Now, hypervalent only occurs on the central atom. The outside ones stay with the octet rule. So let's do a few examples. All right, PCl5. So if we have PCl5, PCl5 is going to give us 5 for phosphorus and 5 times 7 for each of the fluorines for a total of 40 electrons. We're going to put the phosphorus in the center with the chlorines around it. Where they actually go, we'll deal with in a different section. And we've got this. So first of all, phosphorus sees a total of 10 electrons, which we agree is more than 8. If we subtract our 10 here from our 40, we're going to have 30 left over for lone pairs, and we really are going to count 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. And that is a structure for PCl5. It is a hypervalent or expanded octet. It exists. It's relatively stable. If we do selenium with 6 bromines, selenium is in group 6, so that's 6 electrons with 6 bromines, which is 6 times 7, because bromine's in group 7, for a total of 48 electrons. With the selenium in the middle and the bromines around it, at some point you're going to get pretty crowded. Put our total number of bromines around this, and then we start putting in our lone pairs. First of all, we have a total of 6 bonds. So if we subtract 6 times 2, which is 12, we're going to have 36 electrons left over, and we're going to put them in on the bromine. And as we put them in on the bromine will complete its octet. We will leave the central atom with an expanded. Again, the central atom is the only atom that's ever going to have an expanded or incomplete octet. The rest of them will always obey the rules. And when we're finished, we have 48 electrons, and we really do have 6 bonds on selenium for a total of 6 pairs of shared electrons. Expanded octet. Let's do a couple more. IF5 and XEF4. IF5 is going to be 7 plus 5 times 7 for a total of 42 electrons. Iodine's in the middle. We're going to put the fluorines around it. When we put the fluorines around it, I'm going to do it like this. I'm going to realize I've got 5 bonds, so I'm going to subtract a total of 10 electrons, giving me 32 electrons left over. I'm going to start by putting them on the fluorines, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay, which is 30. Well, I have 32 total. I can't put any more on the fluorine. The fluorine is never going to have an expanded octet, so the remaining have to go around the iodine. And on this case, in the IF5, iodine has got 5 bonds and 1 lone pair. If we have xenon tetrafluoride, and note our elements in group 8 are no longer called inert gases. They are called noble gases because in the 1960s we discovered we could make compounds out of them. And we're just going to count their valence electrons. Xenon's in group 8, so we've got 8. Plus 4 times 7 is going to be 28, plus 8 is going to give me 36 electrons. So if I take and put the xenon in the middle, and I bond the 4 fluorines to it, I'm going to put the lone pairs on fluorine, 2, 4, 6, 2, 4, 6, 2, 4, 6, and 2, 4, 6. If I do that, I'm going to realize that I have a total of 32 electrons that I've used now in bonding. If I take a look at that, I've got 4 electrons left over. I can't touch the fluorines. They have obeyed the octet rule. And the remaining 4 electrons go on xenon, such that xenon has 4 bonds and 2 lone pairs. It actually works. Going to be an expanded or hypervalent octet. So we're going to do one last one, and we're going to do ICl4 minus, and this is ICl4 with a minus. So if we count our electrons, we've got 7 from iodine plus 4 times 7 from the chlorine. The negative means we add 1 more electron, so we're going to have a total of 36 electrons. If we put the iodine in the middle with the chlorines around it, we're going to start with that. We put the lone pairs on the chlorine. Note we've got 8 electrons so far, so 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 electrons right there. We've got 4 left over, so we're going to have the lone pairs on the iodine. So iodine here is going to have 4 bonds and a lone pair, hypervalent.